All right, you are welcome again. Today, let's talk about partial derivatives. Okay, partial derivatives. Let's take a look at this question. It says if f being a function of x and y is equal to tan inverse of y all over x, we are to prove that the first and second partial derivative of x, the first and second partial derivative of f with respect to x is equal to 2xy all over x squared plus y squared in bracket squared, and b, the first and second partial derivative of f with respect to y is equal to minus 2xy all over in bracket x squared plus y squared in bracket squared. Okay, now please pay attention to this. It's very simple. Let's see how we can solve this problem under partial derivative. Okay, for a recap, what do we mean by derivative? We are talking about rate of change. Okay, but when we talk about partial derivative, what are we talking about? We are talking about when something depends on more than one factors, and when one of these factors changes, there will be a partial change. Okay, yeah. Now when you bring it to the mathematical term, you can say partial derivative. Something depends on more than one factor, and when one of those factors changes, definitely there will be a change, right? Good. Now let me bring out a practical example for us to understand what we mean by partial derivative. Let's see, we have what we call the volume of a rectangle. Volume of a rectangle. And then you know that volume of this rectangle, it depends on the length, the width, and the height. Yes, the volume depends on the length, the width, and the height. So when we are talking about partial derivative, partial changes, the rate of change, it is partial, is when these factors now, this length, the width, and the height, when one of them changes and the other two remains constant or remains the same, there will be a partial change on the V, which is the volume. Okay, that is when we say partial what? Rate of change. Partial rate of change. That is partial derivative. Now, you understand what we mean? Look at this. We have rectangle, and this rectangle depends on three factors: the length, the width, and the height. So at this point, there may be a change on the length. That is to say, the width and the height remains the same. So you see that because of this change on the length, it will affect the volume partially. Again, there could be a change on the width, okay, which will affect the volume. Now at this point, you see that the length and the height remains the same. It remains constant. It doesn't change. And then at another point, you may see that height may change, okay? And then length and width will remain constant, will not change. So this is what we call partial derivative. Now let's take a recap. When we have something like this, z is equal to 4x, and you want to find the derivative of z with respect to x, okay? You see, we have 4x. At this point, you see that 4 is constant, right? So when you differentiate this with respect to x, we are going to have the z all over the x is equal to 4, right? Yes. Now let's see another instance where we have z is equal to xy. Z is equal to xy, and we are asked to find the partial derivative of this z with respect to x. So at this point, the variable that is changing is x. So that is to say the other variable remains the same. is like a number. It is a constant, right? You see the way we hold this 4 as a constant is the same way we regard this y as a constant. So when we have z is equal to xy, and we differentiate this z partially with respect to x, we are going to have y. Okay, just take a look at this. Z is equal to 4x. We differentiated, and then we have 4, right? Because 4 is the constant. And then here we have z is equal to xy. We differentiated with respect to x. Then we have what? Y. Good. Now let's go again. The question, or the original question we are solving, is f is equal to tan inverse of y all over x. The original equation is f is equal to tan inverse of y all over x. So at this point, we are going to use chain rule to differentiate this. Okay, now before we continue, let me also give you some few tips again. When we are talking about partial derivative, this is the symbol. Okay, we have partial f all over partial x, or you can have f subscript x. F subscript x, that is the partial derivative of f with respect to x. And then you can have the second partial derivative of f with respect to x. That is the first and the second partial derivative of f with respect to x. So you can also have it f subscript xx. And then again, you can also have the second partial derivative of f with respect to x and with respect to y. So you can also write it like this: f subscript x y. All right, now let's go. Here we have f is equal to tan inverse of y all over x. Now let's go forward and apply the chain rule in differentiating this. So that means somewhere we're going to say let u equal to y all over x. In this place we have tan inverse of y all over x. So this inside this content, okay, this y all over x, let's call it a letter u. So that means we have u is equal to y all over x, right? So as we call it out, let's differentiate it partially with respect to x. So when we differentiate this partially with respect to x, that means we have u subscript x. We're going to have minus y all over x squared. I think you know how we get this, right? Yeah, we have this is the elementary, or this is the basic of differentiation. I'm very sure that you got this, right? Now let's continue. You know, here we say that we have f is equal to tan inverse of y all over x, right? And we just declared a variable u to be y all over x. So that is to say we now have a new function. F is equal to tan inverse of u, no longer y all over x, because we have declared a variable, right? Good. So at this point now, f is now a function of u, no longer a function of x and y, but a function of u. So what do we do now? We differentiate this function f partially with respect to u. Okay, so when we do that, what are we going to have? We're going to have 1 all over 1 plus u squared. Okay, how? This is a basic function. Okay, this is what? It's a basic function. So the derivative of tan inverse of x is 1 all over 1 plus x squared. So the derivative of tan inverse of u is 1 all over 1 plus u squared. Is that clear? Good. Now let's continue. Let's apply the chain rule properly here. Okay, let's apply it fully. You know, we declare the variable somewhere and we say u is equal to y all over x, and then a new function becomes f is equal to tan inverse of u, and we differentiated these two, right? So when we multiply these two together, it's going to give us the partial derivative of f with respect to x that we are looking for. So this is it. We say that the partial derivative of f with respect to x is the partial derivative of f with respect to u multiplied by the partial derivative of u with respect to x. Right? Good. Now let's go. Look at it. We have gotten these values, right? Let's bring it together. That means we have the partial derivative of f with respect to x is equal to, here we have 1 all over 1 plus u squared. That is for what? The partial derivative of f with respect to u. Then multiply by the partial derivative of u with respect to x, where we have minus y all over x squared. So let's bring this together. We'll multiply this together. We're going to have that the partial derivative of f with respect to x is equal to minus y all over x squared open bracket 1 plus u squared. Are we together? Yes. Now let's continue. In the denominator we have x squared and we have bracket. Let's use this x squared to open the bracket. When we use the x squared to open the bracket, we're going to have minus y all over x squared plus x squared u squared, right? Yes, but you remember that u is y all over x. Let's replace u with y all over x. So when we replace, we're going to have that the partial derivative of f with respect to x is equal to minus y all over x squared plus x squared open bracket y all over x in bracket squared. You remember that u is squared, right? Good. So the content of this bracket, which is y all over x, is going to share the squared, right? So when they share it, this is what we have. We have minus y all over x squared plus x squared open bracket y squared all over x squared. Look at it here. This x squared outside this bracket, we cancel the x squared in the denominator, right? It's going to go. So when we cancel out, we are going to have that the partial derivative of f with respect to x is equal to minus y all over x squared plus y squared, right? Yes, good. Now let's go. We have gotten one step. So from here, we go further to find the second partial derivative with respect to x. Okay, so going further, we are going to apply the quotient rule. Okay, the quotient rule. Okay, and I'm very sure you still remember the quotient rule, right? Okay, let's take a look at this. Maybe you have y is equal to u of x all over v of x. So for you to differentiate this using quotient rule, we're going to have that dy dx is equal to v du minus u dv all over v squared, right? Good. Now let's apply it here. Here we have that the partial derivative of f with respect to x we have is minus y all over x squared plus y squared. So the numerator is our u and the denominator is our v, right? Good. So here we bring the numerator up, which is x squared plus y squared in bracket, right? Good. Now we differentiate the numerator, which is the u. So when we differentiate y with respect to x, differentiate y with respect to x partially, is going to give you 0. Okay, we regard it as a constant. Good. So here we're going to have 0, then we have minus. Now your u, which is the numerator, we have y. Then we differentiate the denominator with respect to x. So when we differentiate x squared plus y squared with respect to x, what are we going to have? We're going to have 2x, right? That is in the numerator. And then in the denominator, where we have v squared, we're going to have x squared plus y squared in bracket squared, right? Good. So that is to say that the first and the second partial derivative of f with respect to x is this, right? Good. Now let's simplify the numerator. So here we have x squared plus y squared in brackets multiplied by 0, which is going to give us 0. Then we have minus, we have y open bracket 2x. So in the numerator, we're going to be left with minus 2xy. But remember, we have minus outside. So this minus outside multiplied by the minus inside is going to give you positive. So therefore, the first and the second partial derivative of f with respect to x is giving us 2xy all over x squared plus y squared in bracket squared. Are we together? Yes. Okay, here we have finally gotten the first part of the question. Okay, now please pay attention. The second part is not the same as this first part, there is still little mathematical operation that we're going to perform. So let's complete it. Okay, let's take a look at the second part. The second part says we should prove that the first and the second partial derivative of f with respect to y is equal to minus 2xy all over x squared plus y squared in bracket squared. Right, now let's go. Here we have f. From the function that we have f is equal to tan inverse of y all over x. Right, good. So here we apply chain rule as usual. So we're going to declare a variable u. We say that u is equal to y all over x, right? So at this point, we are differentiating partially with respect to y. You know, the first one we differentiated the first and the second with respect to x. So in this b part, we are differentiating the first and the second with respect to y. Okay, so here as we declare the variable u is equal to y all over x, so we are going to differentiate this y all over x with respect to y. Okay, so when we differentiate this, we are going to have 1 all over x. Okay, you know, this is a basic, this is elementary differentiation, right? I'm very sure you can do it. Now let's go. Okay, in this place where we have our function f is equal to tan inverse of y all over x, and we have declared a variable u to be y all over x. So that is to say that our function, our new function, is f is equal to tan inverse of u. Okay, so here now the function f is no longer a function of x and y, it's now a function of u. So we are going to differentiate this f partially with respect to u. So when we do that, we are going to have 1 all over 1 plus u squared, and we have said this earlier that this is a basic function, right? This is a basic function. The tan inverse of u is 1 all over 1 plus u squared. Now let's go. Okay, so applying the chain rule properly, where we say that the partial derivative of f with respect to y is equal to the partial derivative of f with respect to u multiplied by the partial derivative of u with respect to y. Okay, good. Now let's go. I think these two things, these two partial derivatives, we have gotten them already. Let's bring them and multiply together. So we are going to see that the partial derivative of f with respect to y is equal to 1 all over 1 plus u squared multiplied by 1 all over x. Right, good. Let's combine this together. Let's multiply it. So when we multiply, we're going to have the partial derivative of f with respect to y is equal to 1 all over x open bracket 1 plus u squared. All right, yes, good. In the denominator, let's multiply. Let's open the bracket. So when we open the bracket, we are going to have 1 all over x plus x multiplied by u squared. But you remember that u is y all over x. Let's replace it. So here we're going to have that the partial derivative of f with respect to y is equal to 1 all over x plus x open bracket y all over x in bracket squared. Now this y all over x in bracket is going to partake in the squared, right? So when I partake, we are going to have 1 all over x plus x open bracket y squared all over x squared. Now pay attention to this denominator. Here we have x open bracket y squared all over x squared. So the x is going to cancel, the x outside is going to cancel the x inside. All right, so we are going to be left with y squared all over x. Let's combine the denominator together. So when we combine the denominator together, we are going to have the partial derivative of f with respect to y is equal to 1 all over x squared plus y squared all over x. When we combine it together, we're going to have 1 all over x squared plus y squared all over x. Good. Now pay attention to this. Pay attention to this. You know, this expression like this is the same thing as saying 1 divided by x squared plus y squared all over x. And then when we want to perform this operation, this division is going to turn to what? Multiplication. And then we're going to have inversion. So the denominator is going to come up to numerator, and the numerator will go down to denominator, okay? So that means we have 1 times x all over x squared plus y squared, right? Good. So therefore, we conclude that the partial derivative of f with respect to y is equal to x all over x squared plus y squared. Are we together? Yes. Now let's go. Lastly, let's take a look at the second partial derivative of this function with respect to y. Okay, going again, we are also going to apply the quotient rule, and then I'm very sure you are very familiar with the quotient rule, right? Look at this. Good. Now let's go. Here we have our x to be our numerator, that is our u, and then x squared plus y squared to be our v, right? Good. Now let's go. We bring our v up. So our v, which is x squared plus y squared, we bring it up. Then we differentiate the numerator, which is x, with respect to y. So when we differentiate x with respect to y, is a constant. It's going to give us 0. Then we have minus. We have our u, we bring it, which is x. Then we differentiate the denominator with respect to y. So when we differentiate x squared plus y squared with respect to y, remember, partially, it's going to give us 2y. That is to say that x squared is a constant. It's going to give you 0, right? Good. Then the denominator, which is v, we have v squared. So here we have x squared plus y squared in bracket squared, right? Yes. Now let's simplify the numerator. In the numerator, we have x squared plus y squared multiplied by 0, which is going to give us 0. Then we have minus x, open bracket, 2y. When we multiply this, it's going to give us minus 2xy. So therefore, the first and the second partial derivative of the function f with respect to y is equal to minus 2xy all over x squared plus y squared in bracket squared. All right. Yes, we have solved. We have proved that the function f is equal to tan inverse of y all over x. We have proven that the partial derivative of this function, the first and the second partial derivative of this function with respect to x, is giving us 2xy all over x squared plus y squared in bracket squared. And then the first and second partial derivative of this same function with respect to y is equal to minus 2xy all over x squared plus y squared in bracket squared. All right. Yes. Thank you very much for watching.